Hello, my name is Vanessa Castañeda and this is my project, The Holy Ascent. So my function is r of x equals x minus 1 times x minus 2 times x minus 3 all over x minus 2 times x minus 4 times x minus 5. And here is an image of my graph from Desmos. So does r of x meet the criteria? Yes, it does. Because r of x is in the form of f of x over g of x, it is a rational function. F of x and g of x are polynomial functions. F of x and g of x each have 3 rational roots, and r of x has 2 rational roots, which are x equals 1 and x equals 3. R of x has a vertical asymptote at x equals 4 and x equals 5. R of x has a horizontal asymptote at y equals 1. R of x has a removable discontinuity at x equals 2, showing that it does meet all the criteria. Here is a detailed version of my graph. Here you see that I have both vertical asymptotes at 4 and 5, a horizontal asymptote at y equals 1, and then here I have my intercepts. I have a y-intercept at 0.15, x-intercept at 1 and 3, and then the important limits are as x approaches 2, the limit is negative 1 over 6. As x approaches 4 to the right, it is negative infinity. As x approaches 4 to the left, it is positive infinity. As x approaches 5 to the right, it is positive infinity. And as x approaches 5 to the left, it is negative infinity. So here is a blown up version of this section specifically. So here we see that at 2, the graph is undefined because there is a removable discontinuity. There's a hole here showing that all at 2 it is undefined. So derivatives, to find the first derivative, I would use the quotient rule since my function is in the form of a fraction. So quotient rule is derivative of u times v minus derivative of v times u all over v squared. And here you see I have it in that format. And then I would multiply and then I would simplify it by combining like terms, and then my final answer is this, which is negative 5x squared plus 34x minus 53 all over x to the power 4 minus 18x to the power 3 plus 121x squared minus 360x plus 400. Now to find the second derivative, I would basically do the same thing and also use quotient rule because it is in the form of a fraction. And to get the second derivative, I would be getting the derivative of the first derivative. So here you see I have it in the format of quotient rule, and then I would just multiply and combine like terms, and I get this huge fraction because there's evidently a lot of numbers here that I have to multiply. So next, I'm going to do an analysis of my graph. So here's my graph again from Desmos. There's x-intercepts at 1 and 3, a y-intercept at 0.15, which you see here, and then the critical points are x equals 17 plus 2 root 6 over 5, x equals 17 minus 2 root 6 over 5, x equals 4, and x equals 5. To find these critical points, I set the derivative equal to 0 and solve for x. The graph is increasing from negative infinity to 3. It is decreasing from 4 to positive infinity, and there's a removable discontinuity at x equals 2. Next, mean value theorem. So the problem I have come up with is state whether the function satisfies the hypothesis of the mean value theorem on the given interval, and if it does, find each value of c in the interval a to b. So here's my function of r of x again, and I've chosen the interval from 0 to 1. So to solve this problem, here I have my function again, r of x, and we know that the function is continuous on the interval of 0 to 1 because we see that on the graph. And we also know that the function is differentiable because I just did the derivative about 2 slides ago. So since the function is continuous and differentiable, it does satisfy MVT. So now solving it, we have to solve for c. We would use rate of change formula, which is r of b minus r of a over b minus a. Here I've shown that f of r of b is negative 1 over 6, r of a equals negative 53 over 400, and b minus a is 1. So then I would plug it in here, so it would be r prime of c equals this, which is r of b minus r of a over b minus a, and that equals negative 41 over 1200. Then for the derivative, which is r prime of c, I would change x for c and then solve for c, which is approximately 4, negative 12, 8, and positive 12. Now IVT. For this, I've chosen the root x of equals 3 to apply to IVT. So I would need to set r of x equals to k somewhere in the interval that I've chosen. 2.5 to 3.5, I chose this because it does not contain 2, which is a removable discontinuity, and it does not include 4 and 5, which are vertical asymptotes. So I would need to evaluate at the endpoint, which is 2.5 and 3.5, and plug it into the original function, which is negative 0.2 and 5 over 3. I have also chosen that k equals 0. So since 0 is between negative 0.2 and 5 over 3, r of x is continuous. So IBT guarantees that there exists at least one number c in the interval 2.5 to 3.5 that r of c equals 0. We use the fact that 0 is the root of the function to prove that IBT guarantees it existed. So now, extreme value theorem. I've restricted the domain to 0, 5. I need to use the derivative of this to find the absolute minimum and absolute maximum, and EBT ensures that. So I find the derivative set equal to 0 to get the critical points, which we already found, and here they are again. So I set these critical points and I plug them back into the derivative, and for here, 17 plus 2 root 6 over 5 is positive. 17 minus 2 root 6 over 5 is negative. So that means 17 plus 2 root 6 is an absolute maximum. And 17 minus 2 root 6 is an absolute minimum. Now, lastly, we're looking at the equation of a tangent and normal line. To find this, the point I have chosen is 0, 0.15 because it is a y-intercept, making it easier. I will need the derivative, and I need to find the slope first. So to do that, I would plug in my x value into the derivative as x to get the slope, which here is negative 0.1325. And to plug it into the equation, I would use y minus y1 equals slope times x minus x1. Here I have that here, it's y minus 0.15 equals negative 0.1325 times x minus 0. Then for the normal line, it's basically the same thing, but we already have the slope, half of it. To find the full slope, I would need to do negative reciprocal, and that is negative 1 over 0.1325. Actually, positive 1 over 0.1325. Then I would use the same formula, and here is the normal line. And then here I have a picture of the graph from Desmos, and the blue line is tangent line, and the black line is the normal line. So that's all for today. Thank you for listening. I hope you learned a lot, and have a good day.